Hey everyone, how's it going? So up to this point we have talked about sequences and then we did arithmetic and geometric finite series. Now the next step is going to be, can we go to the infinite? So we've got Buzz Lightyear here saying to infinity and beyond, and I put a question mark. The question is, can we represent an infinite sum with a finite number? Can we take something that's infinite and represent it with something that's finite? And our initial thought is no, because if it's infinite, it keeps going and going. But we're going to see here that there are times where we can represent something infinite with something finite. And the question is, when can we and when can't we? Let me just show you an example. Right here we've got a sum. We're going to start at 1 and go see if we can go to infinity and add it up. And again, originally we'd think, you can't add up something infinite. Well, let's just give it a chance here and watch this. What we're going to do is we're going to take 3 over 10 to the k. So what we're going to do is let's plug in 1. So that will be 3 over 10, because 10 to the 1 is just 10. And then now I'd go to the next one and we plug in 2. 10 squared is 100. Then we're going to go 10 to the third. 10 cubed is 1,000. We're just adding on a 0. And we're just going to keep doing that over and over again. So then we get 3 over 10,000. And then we get 3 over 100,000. And it's just going to keep going and going and going and going. Well, maybe it's not quite obvious. So let's write this as a decimal. Here, 3 over 10 is just 0.3. 3 over 100 is 0.03. 3 over 1,000 is 0.003. And hopefully you're seeing a pattern here. This is 0.003 and then 0.00003. And if I add those together, what I'm going to get is 0.33333, and then that's going to keep going forever, which, what is that? That is 1/3. So what we've just done here is I have this infinite sequence, and I was able to add it up, even though it's infinite, to represent it by a finite number. Isn't that pretty cool? All right, so that's the idea of what we're going to be looking at here, okay? We're going to be looking at sequences and seeing, could we add these up? Now, the trick is sometimes, most of the time, it won't be able to work. But it will work if it's approaching a limit. Let me show you a different example here. Let's just look at this geometric sequence here. We go from 4 to negative 4/3 to 4/9 to negative 4/27, and then you kind of start to see the pattern here. We're doing 4 and we're timesing it by negative 1/3 to a certain power here. Because we start out with 4, and how do we get from 4 to negative 4/3? You're timesing it by negative 1/3. And then how do we get from negative 4/3 to 4/9? You're timesing it by negative 1/3. So this is geometric. Our common ratio here is negative 1/3. Now this, instead of being infinite, this is what we're going to call a partial sum. What this one did is, what we're doing here is we're basically saying, you know what, let's just see what does this add up to for the first 11 terms. You might look at this and say that's a 10th term, but remember you usually do n minus 1, and so that would be 11 minus 1 is 10, so that was the 11th term. So if I take these first 11 terms and add it up, what are we approaching? What are we getting closer and closer to? And you can see it's really close to 3. It's not exactly right at 3. But this was only a partial sum. What if we kept going? What if instead of going towards, or stopping at 11, what if we went towards infinity? What if I make this number here higher and higher and higher and higher, and I raise it up? Well, this sum is going to get closer and closer and closer to exactly 3. And you can actually see that right here. Now, if I'm looking at the limit, what is this approaching if we're letting, if we're going towards infinity here, okay? Now, infinity is a really big number, right? If we look at our formula that we came up with last time for geometric series, for finite geometric series, if we start plugging, instead of letting n be 11 or a number like that, if we look at just what if it's a really big number, what will it turn into? Well, negative 1/3, if I raise it to a really big number, it gets smaller and smaller and smaller. So if I raise it to infinity, that's just going to turn into 0. And when I use this formula we came up with last time, it turns it into 3. So what we have right here are just two examples of how if I take something that's infinite, if it has a limit that it's approaching, then we can actually represent that infinite sum as a finite number, which is 3. Now let's just go and do some easy examples. You're not going to have to do anything too crazy. I think the major challenge is just coming to terms with the fact that you can add up something that's infinite to something that's finite, but it only applies in some situations. Alright, so this is in your notes. It just kind of goes over the basics of what an infinite series is and how we can tell if it's going to converge or diverge based on partial sums, which is kind of that example we saw there with example 2, how we saw it was getting really close. I think it was 3. Was it 3 or 4? It was getting really close to 3, but then if we were to look at even bigger partial sums, it was getting even closer and closer. So then as we look at big picture heading towards infinity, then it's going to approach 3. Let me just go over some of these things here. If we've talked about converging and diverging before. Converging is when it's approaching a limit. Diverging is when it's not. It's going up towards infinity, going down towards infinity, or doing something weird that's not approaching a limit. We like it to converge. The question is, when does it diverge or when does it converge? Think about an arithmetic series. What makes an arithmetic series arithmetic is that it has a common difference. You're always adding or subtracting the same number. So let's start with an easy one. If I took 2, 4, 6, 8, 10, 12, that is going to be arithmetic, so I'm always adding 2. Now the question is, could we add that up as a infinite sum? If I'm just going to keep going and going and going and going here towards infinity, could we add that up? And the answer is no, because it's always adding something onto it. It's always adding 2, adding 2, adding 2. So that's going to diverge, okay? And that's true for all arithmetic series. They diverge, which means we can't look at them on an infinite scale. Now, geometric will diverge sometimes. For example, let's just look at this. 2, 4, 8, 16, 32. This is going to just be times by 2. It's geometric, common ratio here. What makes it geometric is you have a common ratio. You're timesing by the same thing. In this sense, it was 2. When I times by 2, times by 2, will I be able to add this up as an infinite sum? And hopefully you're looking at it and you're saying, no way, because then you're going to have 64, and then you're going to have 128, and it's just going to get bigger and bigger and bigger, and you won't be able to add that all together. So in this sense, this one would diverge. But watch this. What if I do 2, and then I go to 1, and then I go to 1/2, and then I go to 1/4, and then I go to 1/8, and then I go to 1/16. What is my common ratio here? Hopefully you see the ratio is 1/2. I times by 1/2 to get here, times by 1/2 to get here. Is this approaching something? What is the limit of this sequence? Is it there a number it's going to get closer and closer and closer to? And hopefully you can start to see that after this would be 1/32, then 1/64, and it's going to get closer and closer to 0. This converges. And since it converges, we can actually go and add up this infinite sum here and represent it, even though it's infinite, as something finite. So our big takeaway, arithmetic series, they're out. We're not going to deal with them on an infinite scale. Geometric, we're going to work with if it converges. Well, when will it converge? The answer is it converges if your ratio, if the absolute value of your ratio is less than 1. Your ratio might be negative. That's why we're taking the absolute value of it. So what we saw in this last example here was that my ratio for this first one was 2. 2 is bigger than 1, so it diverges. For the second one, the ratio was less than 1. It was 1/2. Since it was less than 1, it converges. And since it converges, it means we can find the sum of the infinite geometric series. Now, you would expect that if you're going to add up something that's infinite, it would have a really complicated formula. And the truth is it doesn't. It's actually the easiest one you've seen so far. You take a over 1 minus r. A is your first term. R is your common ratio. And your ratio just needs to be between, the absolute value of your ratio needs to be between 0 and 1. So let's do a couple of examples here. Evaluate each infinite geometric series described. When it says evaluate, it means add it up. So let's look at this. I'm told it's geometric. That means I have a common ratio. My first term is -3. And then I'm going to times that by 3, times the next one by 3, and keep timesing by 3. Let's just write out a couple of terms here. -3 times by 3 is -9. -9 times 3 is -27. -27 times 3 is -81. Now the question is, could I add this up on an infinite scale? That's plus -27 plus -81. Will this converge? Well, you can kind of see already it's just getting more and more negative. It's going, I think the next one would be -243, and then it's just going to keep getting more and more negative, and I wouldn't be able to add that up. This one is going to diverge because look at the common ratio here. The absolute value of our common ratio is what? What's the absolute value of -3? It's 3. Is 3 bigger or smaller than 1? Since it's bigger than 1, it's going to diverge. So that means we can't evaluate. We can't add it up because it's going to be infinite. Okay, well let's look at number 8. Okay, on this one I'm going from 4 to 12/15ths. From 12/15ths to 36/25ths. And from 36/25ths 108 over a 125. Now, I'm told this is geometric. That means there should be a common ratio. Now, if you don't know how to find the common ratio, you just divide a term by the thing before it. Divide a term by the thing before it, and you should be able to figure out what the common ratio is. Just to help, let's take the trickiest one here, okay? 108 over 125. That was the term here. We're going to divide that by 36 over 25. And we have a complex fraction, a fraction divided by a fraction. To simplify that, we're just going to do keep, change, flip. In other words, we're going to multiply by the reciprocal. Alright, now when I do that, I'm going to try to reduce this, okay? 25 is 5 squared, and 125 is 5 cubed. So if I can basically cross those out and just leave a 5 there, okay? Same with my, let's see, 108 over 36. I want to say that reduces to 1/3, okay? So I'm going to cross this out, and say 108 divided by 36 is 3. So this becomes 3/5. My ratio here is 3/5. Now let's see if that makes sense. If I go 4 times 3/5, I get 12/5, and that checks out. 12/5 times 3/5 is going to be 36/25. There we go. Here is our common ratio. Now, based on our ratio, will this series converge or diverge? The way we know is by looking at the ratio. since 3/5 is less than 1, we know that this is going to converge. It's going to have a limit. Now, we're asked to actually find it. When it says evaluate it, we need to find what that limit, or find what we would get if we added it all together. Okay, so we need to now use a formula we got from the last page and add those together. The formula, if you remember, just says that your sum of your infinite series here is going to be your first term over 1 minus your common ratio. So now our first term on this, let me scroll up so you can see again, is 4. And our common ratio we found was 3/5. Now if I do 1 minus 3/5, that's going to be 2/5. Again, I've got a 4 over 2/5. I'm going to keep change flip there. So that would be 4 times by 5 halves. 4 times 5 is 20. 20 divided by 2 is 10. What that means is that if I were to go and add up this entire infinite sequence, even though it's infinite, it would add up to 10. Pretty cool. I hope that makes sense. The big takeaway here from these two problems is based on the common ratio, it will converge or diverge. If the absolute value of your ratio is greater than 1, it will diverge. If the absolute value of your ratio is less than 1, then it will converge. And if it converges, you can use the formula to add up the series, even though it's infinite, and get a finite representation of the sum. Okay, let's do 2 more, and then that is it. Okay, determine if each geometric series converges or diverges. So how do we do that? We're going to look at the common ratio. Is the absolute value of the common ratio greater than 1 or less than 1? So to do that, we can go through and you can look at it and say, okay, how am I getting from 1 to 1? Or you could divide a term by its previous term. Either one works. Looking at this, I'm fairly confident that it's just the ratio is going to be 1/3. If I times -2 by 1/3, I get -1/3. If I times -2/3 by 1/3, I get -2/9. So my common ratio here is less than 1, so this tells me that this will converge. Now we're not going to stop there. Let's actually evaluate it as well. We'll use our formula and just say we're going to take our first term, -2, and divide it by 1 minus our ratio. 1 minus 1/3 is going to be 2/3. And if we keep change flip, we're going to have -2 times 3 halves, and those cancel to just give us -3. Actually, I think I made a mistake. Let me look at that again, because I'm not liking that. No, that seems right. Okay, hold on. Let me just check when I did this before I got a different answer, so I'm checking real quick. Okay. I believe that's right. If not, I'm going to double check you on that later. Does the idea, though, that if the ratio is less than 1 make sense? I hope so. And if so, you can just plug it in and get an answer. Okay. Lastly, on number 10, does this converge or diverge? Now, this is geometric, which it will be very helpful for you to remember what the explicit formula for a geometric series looks like. You're going to have, you get your nth term by taking your first term, timesing it by your ratio to the n minus 1. Well, if I'm looking here, this is going to be my ratio. The absolute value of -3 is 3, which is greater than 1, so this is going to diverge. So I'm not even going to be able to add that together. All right, now you might be asking, why are we doing this? Well, actually, you use these in Calc 2 when you're trying to find the area under a curve. over an infinite length? Can you sum up the area of a curve over an infinite length? And the answer is yes, if it converges. So this will come into play as you get into your future classes. So it is pretty important. So that's everything you need to know for series. What you're going to do now is go on to School City and take the series quiz. If you don't do well the first time, there is a retake, but make sure you study up. And if you have any questions, make sure you ask either myself or Mrs. Reed. All right, thanks for tuning in, and we'll catch you next time.